Thank you. Thanks a lot for the invitation, and also I want to thank my co-author Michel, Jaboyedoff, Antoine, and Lifei and Wei Liu, who gave me some new documents that I have included into this presentation. So today I will talk about the use of thermal imaging in rockfall assessment. And I was just asked, maybe but very short, to say a few words about where I come from. Basically, I am a Swiss and a geologist. I studied in Lausanne. I did a PhD actually more in water-rock interaction, rock weathering, and it's still a topic I am interested in. It's how rock weathering influences landslides. But during this PhD, it was 25 years ago, there was a new technique coming. It was radar interferometry. And so after my PhD in geochemistry, I decided to do some interferometry, and that's how I started to do remote sensing. And with this, I left the university to work for the Geological Survey of Norway during about 6 years, doing a lot of landslide mapping, monitoring, remote sensing. And I came back to my home university in Lausanne in 2009 in the group risk here, so at UNIL. So that's just short. That's not very interesting, but that's what I did. Okay, what I am going to talk about today is thermal imaging, and I have to introduce some basic principle, and you will see that the most difficult one is what is temperature, and then like that I can explain what thermal images actually is and what does a thermal camera actually record. And then I will pass to some case studies, to some applications of thermal imaging in rock slope stability. So I have here 6 little case studies, different research which have been done using thermal imaging. Deformations, rock bridges, thermal erosions in sedimentary rocks, another research on the parameters which influence thermal images, the detections of cracks in winter, and finally how thermal images can be used during rock mechanical tests. So it's just in 45 minutes, it will be just an overview of these different things. So let's pass to the problem. So during this presentation, you will see a lot of, several examples of studies that we did in the Yosemite National Park in California. And you maybe know these big walls. And this is the thermal image of this big wall here. And okay, that's typically what you have when you do a picture with a thermal camera. You have nice colors with a color scale of temperatures here from 19 to 35 degrees Celsius. So you can see that if you see my cursor, I hope you can see that here there is a warmer place. We can imagine that the sun is hitting this place. But you may also see a bit strange things. First thing is that you can see that the top here is much colder than the base, maybe 10, 15 degrees colder. And the wall is only 1 kilometer high, so it's a strange gradient of temperature. And there are different things in an image like that you may think, oh, but is the temperature recorded by the camera the real temperature? If I go with a thermometer to measure the temperature here on the top, will it be the same that on the camera? And to better explain that, I just going to show you a small experiment I did just in front of the university here in Lausanne with 3 spheres. You see 3 bowls in different materials. The bowls have diameters about 30 centimeters. One is in terracotta. It's that will be the analog for a rock, a piece of rock. One is covered by an aluminum sheet, and the third one is covered by black tape. And you see that was, I would say, a normal day. The air temperature is about 20 degrees, and it's a blue sky, so no clouds, so nothing special. And now, if I take a thermal image of these 3 spheres, here's the result. So there are strange things. First, the first thing you can see is that the temperature goes from minus 60 degrees to plus 60 degrees. You have minus 60 degrees on the top of the aluminum and almost plus 60 on the top of the black tape bowl. So first, we have a strange range of temperature. So the first question, the first thing that we see, you can imagine that if you put your hand here on the top of the aluminum bowl, you will not feel it's frozen. It's not at minus 60 degrees. So what is this minus 60 degrees coming from? And so the first thing we can say that the temperatures recorded by a thermal camera is not the true temperature, at least the temperature as we are used to work with. And another thing we can see is that the material has a strong influence on the temperature. The aluminum seems to have to show completely different temperature from the black tape and from the rock or terracotta material. And the last parameter we can see on this picture is there is a strong influence of the geometry, because here are the orientation of the face. Here, between the top of the aluminum and the base of the aluminum bowl, there are almost 80 degrees of difference. Here, 20. Here, there is a small difference between a fringe here and the rest of the bowl, which is at 30 degrees. So geometry, material, has a strong influence. And the other message you have to keep in mind is that what the temperature which is recorded by the camera is maybe not what we are used to call temperature. And so that's the important question, is what is actually temperature? In physics, it's actually not so easy questions. There are 2 fields of physics who are dealing with that. It's thermodynamics and statistical mechanics. And so I'm not going to do a course in physics, so I try to simplify as much as I could, but I need to introduce a small concept of temperature. So in matter with temperature over 0 degree Kelvin, the particles, can be atoms or molecules, they move, which means they translate, they collide, they vibrate, they oscillate. And temperature is a measure of this agitation. And then comes an important point. There are different ways to measure this agitation. One can measure the velocity of the particles. It's called the kinetic temperature. Or one can measure the electromagnetic radiation generated by this movement, by this agitation, because this agitation makes oscillation in the density of electron of the particles. And when you have a charge changing, it generates electromagnetic radiation. And that's another way to measure this radiation, this temperature. It's called the radiant temperature. So if I just now explain what is the kinetic temperature. The kinetic temperature is our usual temperature, the one we know. So when the temperature is over 0 Kelvin, the particle moves. When the particle moves, they have an energy. It's simply the kinetic energy. And the temperature, the kinetic temperature, is proportional to the average kinetic energy of the particles. And you know that's actually, because that's how classical thermometers works. The atoms of mercury of the thermometer, when the temperature increase, these atoms, they move faster. And by consequence, they occupy a larger volumes. And so the level in the thermometer rise up. So the level of mercury in a thermometer is an indirect measurement of the kinetic energy of the mercury atoms. That's a kinetic temperature. That's our usual temperature. Let's have a look to the radiant temperature. The radiant temperature, it starts with the same thing. The particle moves. When they move, collide, vibrate, oscillate, it induces a change in electron density because the atoms get closer, farther, and then you have this change in electron density, and it generates an electromagnetic radiation. This electromagnetic radiation, its intensity and its wavelength, is a function of the temperature, which means that you can use this electromagnetic radiation to estimate the temperature. And that's what a thermal camera is doing. And the physical law between this relation is the Planck's radiation law, which describes the amount of energy, B here, in function of the temperature, T, for different wavelengths. This equation looks complicated, but actually, except the wavelengths, the temperature, and the energy, all the rest are constants. These are fundamental physical constants. So here we have a function of the energy emitted by an object in functions of its temperature. So what we have to keep of this introduction on temperature is that there are two types of temperature. The kinetic, the true temperature, if you want, the one that we know, and the temperature, the radiant temperature, the one measured by the radiation. And the question are they equal? Are they the same? So the bad news is that most of the time, no. They are if it's a black body. So rocks are not black bodies. They are not very, very far from black bodies. So frequently we can do a kind of approximation. But formally, they are not black bodies. And so, which means that the temperature that we see on the picture is not the same that you would measure with a thermometer on the surface of the rock. And so that's a bit the deal with thermal images, is that we are used to the kinetic temperature, but the thermal camera records the radiant one. So I just want to say a few very short words about this Planck's radiation law. It describes the energy emitted by an object in functions of the wavelengths here, its logarithmic scale, and in functions of the temperature of the object. So for instance, in yellow here, this is the sun. The sun, it's a bit less than 6,000 degree Kelvin. And what you see is that it emits a lot of energy. The peak of energy is in this wavelength here, which corresponds to the visible light. And that's why we have the light, the daylight. Now, if you look at object at the Earth's surface, about 20 degrees Celsius, it's here, you see that the peak of energy is at 10 micron. It's here. So it's a much longer wavelength. And so most of the objects on the Earth's surface, they emit here. They don't emit visible light. And that's the reason why the thermal camera, they record the energy emitted in this range here between 8 and 14 micron. So that's the range of acquisition of thermal camera. So that was for the Planck's radiation law. Now there is another law. It's actually the integral of the Planck's radiation law. What does it mean? It's just the total energy emitted by a body at a temperature T. So for the sun, it's the yellow area below the curve here. It's the integral. And for an object at 20 degrees, that will be the red area here. And the thing which is important here is just to remember that the energy emitted by a body is proportional to its temperature power 4. Sigma is a constant. And why is it important? Because you will see that actually the camera is not recording the temperature, but it's recording the energy which is emitted by the body. What I described now is for a kind of ideal body, a theoretical ideal body that we call a black body. Black body is defined as a body which follows perfectly the Planck's law. In nature, there are not so many black bodies. There are some, and one is pure water. Distilled water, really pure water, here in gray, follow almost exactly the behavior of the theoretical black body. It means that it emits the energy which is described by the Planck's law. Here on the right, this is the case of a rock, a granite. And so what you see that a granitic rock emits less energy than what a perfect black body would emit at the same temperature. And here come an important parameter, which is called the emissivity. The emissivity is the ratio between what the real body is emitting in terms of energy relatively to what the black body would emit for the same temperature and the same wavelength. And this emissivity, why is it important? Because in all the thermal images you do, you have to provide this parameter. And in all the cameras, there is somewhere in your camera an option where you say, okay, this is this emissivity. And so that's a parameter which will come back a lot when you do thermal imaging. So emissivity is the ratio between the energy emitted by the real body over the ideal black body energy. These are typical emissivities of material. So I just put here in red, for instance, for soils, it's about 0.9, granitic rocks, and basalt. Basalt is darker. So a perfect black body would be 1.0. You see water, it's almost 1. And rocks are somewhere between 0.8 and 0.95. So they are not black bodies, but they are not either so far from black bodies. No, just here, aluminium, it's almost 0. So it's the opposite of a black body. And that's something I will show you after what is the consequence of that. So what does a camera actually records, and why is it important to have this kind of concept in mind? Is that the camera do not measure temperature. When you make a picture, you will have a nice scale, color scale in degrees, but actually the camera has done a lot of calculation to provide you the scales. And what the camera is measuring, it's an energy, which is called excitance, but you see it's watt per square meter, joule per second per square meter. It's an energy per second per square meter. And this energy is transformed into temperature. So this is the body here, which has a temperature. What the camera is recording is this energy here, which depends on the real temperature of the object and on the, you see, emissivity of the object. So that's the first thing that the camera records. And now comes the big problem. The big problem is that your object is not alone in the universe. All around the object, there is an environment. There is the sky, there is the sun, there are other objects which also have temperature. It means that this, what we call environment, emits thermal radiation also. And this is E here. This is just one. We group all the thermal radiation in one resulting vector, and we call it E. And this is all the thermal radiation from the surrounding. And part of this energy arrives on the surface and is reflected by the surface. And we can show, it's called the Kirchhoff's law, that the coefficient of reflection is 1 minus the emissivity. And so that's what actually is collecting the camera. It collects both. It collects the energy which comes from the temperature of the work and the energy which is just the reflection of the surrounding. And that's how then you get a temperature. There is, you see, this is the temperature of your image. And it depends on the temperature of the object, thing that we would like to know, but it depends on the emissivity of the object, and it depends on what we call the radiant environment temperature. So all this thermal radiation around the object. And that's why we have sometimes some surprise with thermal images. And now I can explain what happened here with these three spheres and these strange thermal images ranging from +60 to -60. So if we look at the aluminum sphere in the middle, aluminum has a very low emissivity. It means that it's the opposite of a black body. It's like a pure reflector. It's not absorbing, it's just like a mirror, reflecting. And so what is it reflecting? It's reflecting the temperature of the sky. The blue sky has a temperature of about -60 degrees. What you see here, it's a real temperature, but it's not the temperature of the sphere, it's the temperature of the sky. And same thing here, the temperature that we have here is not the temperature of the sphere, it's the temperature of the ground. Now, if we look the black tape sphere here on this side, it's the opposite. It has a very high emissivity. It means that it's almost a black body. It absorbs everything. It absorbs all the radiation, in particular the solar radiation. So the temperature of the sphere increases and it radiates this temperature. It means that here, the temperature that we see on the picture is almost the real one. If you go with a thermometer and measure on the surface, you will find something like 50 degrees. And what about the rock or the terracotta sphere? It's somewhere intermediate. If you go with the thermometer here, you will see that we did that the temperature is about 30 degrees here. But you will not see this fringe. You see here on the image, there is a fringe of about 15 degrees. And if you measure the temperature here, that will be much higher than 15 degrees. So what happened here? Here we have a bit of reflection of the sky. You have this sky radiation arriving on the top here and reflected. And what we see here is a mixture between the real temperature of the sphere and the sky reflection. And that was just to explain you a bit these different types of temperature and sometimes on the picture you see things which seems quite different from what you expect if you go and measure in situ the things. So the temperature recorded by the camera on the image will depend on the kinetic temperature of the object, on the emissivity of this object, and on the orientation of the surface relatively to the surrounding, in particular the sky, the sun, or the ground, for what we are concerned here. So just a few words about the acquisitions, how it's done. So I just put here the different camera that we use usually in Lausanne. There is the small camera pocket. We have a bigger one, and this is the best we have. And of course, we use also a drone's camera. And it goes basically from 200 euros to about 50,000 euros for higher resolutions. I am not going to go in details, but all these cameras use a sensor which called microbolometers. It's a small resistance here. This is a resistance, and this is an array of resistance on the chip. And it collects the radiation at 10 micron, and this, depending on the intensity of the radiation, the resistance varies. And so measuring this resistance, you can estimate the energy arriving on this little piece. The problem is that in thermal camera, you need one resistance like this for each pixel of your image. And it explains why actually thermal camera don't have much pixels. Presently, most of the commercial camera, they have about 1000 by 800 pixels. And this is what I explained before. The camera is recording a component which come from the object, a component which come from the radiative environment. And I didn't mention before, but the atmosphere in between the camera and the object has also a temperature and is also contributing. So when you have a thermal camera, you are asked to define 5 parameters. One is the emissivity of the object. The second one is the environmental temperature. And then you have 3 parameters to characterize the atmosphere, which is the air temperature, the humidity of the air, and the distance in between the camera and the object. That's what you have to define. So in the field, there are different ways to do it. For instance, you will see piece of aluminum, and this acts like a reflector, and you can use this piece of aluminum to estimate the environment radiant temperature. You can put a contact thermometer to compare the temperature and estimate the emissivity of the rock. So there are things that you can do like this when you do acquisitions. That's what Antoine Guérin, my co-author, he's here in Yosemite and one of this big wall, and he puts reflector like this with aluminum that we can see here to estimate these different parameters. Okay, enough theory, let's pass to applications. So let's go to this Yosemite National Park. And this project started there because of that. They have quite a number of rockfalls, and usually this rockfalls happens during the summer, July, August, July, and during the afternoon. Most of the rockfalls there occurs during the afternoon in summer. And just to show you a bit the context, these are mostly granitic bodies with strong exfoliation, like you can see here, and with exfoliation sheets, we call it flakes, which can be from 10 centimeters to few meters thick. And here, another case with a rockfall falling from here. And the problem that they have is that one of the main hotels in the Yosemite National Park is actually just at the foot of a quite active rockfall area. And so Antoine did monitoring of the rock deformation to see how the rock deformed during the day because of the heating. And that's here, he monitored this area here with a laser scanning and with a thermal camera and with different in situ sensors. So he selected a crack here. You can see it's a crack. It's about 10, 15 centimeter open. He put inside different crack meters and sensor to measure the temperature. And he did thermal imaging. And he looked how this crack was evolving when it was getting warm. And here, I just need to, oops, sorry. Oops, how do I start the video? Just. Here. So this is the thermal imaging during the day. So it's, you see, okay. What you see here is that during the day, the temperature of the rock wall can be over 40. Actually, it's more than that, 40, 50 degrees, and it decreased during the night down to 20. So you have a range of temperature of about 20 degrees every day. In the same time, Antoine did laser scanning, and it's in this part here, and you can see the deformation during the day of this rockfall. So I just show you here. Here you can see the hour of the day and the deformation, which is actually the crack opening by crack meter or by laser scanning. And what you can see is that every day, during the night, here it's 8 p.m. During the night, the crack close. And when the sun arrives, the crack open. And next day, it will close and open. And you can see here, it's about 5 millimeters. So it means that every day, the crack open and close like this. And it's a deformation. And there is another side where it's even 1.5 centimeter. So every day, the crack open of 1.5 centimeter and close of 1.5 centimeter. That's, you see, it's really a daily movement. And this daily movement has a strong influence on the stability, on the midterm stability of this kind of flakes, because as you can see here, it's the temperature on this axis, and on the other axis, it's the crack aperture. So when it goes on the right, it means that the crack is opening. And so it makes cycle like this. So the temperature decrease, the crack close. When the sun arrives, the temperature increase and the crack open. And the next day again. But now, if you do the monitoring several consecutive days, you will see that the crack open more and more. Every day, it will open a bit more than the previous day until the crack collapse. And this is the first results that was presented by Colin and Stock on the crack that Antoine monitored, but they didn't do thermal images, they only use a crack meter to do this. But this is the reason why when you have this daily heating, cooling, progressively, it's already a progressive failure, the crack open more and more until it fails. And that was the main reason why most of these rockfalls occurs in summer during the afternoon. Now I pass to a second case study, always in the Yosemite, and this is quite interesting because it's for the detection of rock bridges. So this time we go in this El Capitan rock wall here, and maybe you know things about. So it's about 1 kilometer. It's very famous for climbers. And in this wall, there are what we call flakes. Flakes are sheets of granites like this, very thin, which are sticked on the main wall. And you can see here a famous climber, Alex Honnold, who is lying on the top here of this one here, which is called Texas flake. There, he's just here. And there is another one here. And the question is, how much of these flakes are still keeping it in contact with the main wall? What is the size of the rock bridge on these flakes? And this is boot flakes. So boot flakes is this one. You can see a climber here. And when you see this, you see it's open. But how much of this flake is still keeping it in place? And that's what Antoine was able to demonstrate by thermal imaging. So you have these two flakes here, these two blocks here and there, and the thermal imaging. And you see it here quite well. In this part of the flake here, in the lower part, it's colder than in the central part. And it's also colder in the upper part. There is a profile of temperature here. It's about 2 degrees of difference. And why is it colder? It's because you have the air can pass behind, and it helps to cool the flake. So there is a difference of temperature. And these are the same flakes and the thermal images here. And Antoine, by numerical modeling, was able to determine the size of the rock bridge, which is still keeping the flake in place. And here too, he was able to detect that the main of the rock bridge was here on the base, but there was a small piece of rock still in contact there. And if you look now at the ratio of the surface, you can see it's about 7 square meters for a flake of about 70 meters. So it's 1 to 10. And it's about the same ratio here between 180 square meters over something like 20 meters of rock bridges. And as far as I know, in this work, that was the first time that it was possible to have an image of rock bridges before the rupture. Usually you see the rock bridges, but when it's after the rockfall. And what you see is that 10% is more than enough to keep a piece of rock in places. And after this, Antoine tried to detect flakes that were not visible from that we didn't know it exists. And so here on this slide, you have the boot flake here, the flake we saw before. And on the right of this one, Antoine was able to detect that there were some special patterns here indicating that some part of the rock was cooling too fast, and it means that there is some air passing behind, and then there are some opening, and we suspect that actually here there are some flakes which are already quite well detached. So that was for the detection of rock bridges. And here, why does it work? It works quite well for one reason, is that basically there is only one type of rock, so which means only one emissivity. If there was a mixture of rock, that would be a bit more difficult to see these kind of patterns. And it's very flat, so it means that there is only one orientation, and so only one gradient environmental temperature. And it makes the calculation much easier, and it's actually makes possible just to look at the image. Even if the absolute temperature are not right, the relative temperature are okay. And that's why in this kind of conditions, thermal imaging was very successful. Now I pass to a third case, which is thermal erosion of a cliff. So this is a sedimentary cliff close to Lausanne. It's an alternation of sandstones and marls. So it's about 30 meters high, something like this. And what you can see here, it looks like that. So you have sandstones, the big layers, massive layers are sandstones, and the blackish layers are marls. And Liefey and Caroline Lefebvre did monitorings during several days with different instruments, LiDAR, thermal imaging, plenty of sensor, ground-based sensor, and so on. I will just show you some results of the thermal imaging. So this is one image during the summer of this cliff of the thermal imaging with temperature ranging from 30 to 60 degrees. So what you can see here is that the black shales, they get very warm. Actually, they get close to 60, over 50 degrees. They get very warm. The sandstone with the same exposition, they are much colder. So you have a difference between both. Of course, there are areas with shadows, so it's a bit, you cannot compare this area. But if you compare the sandstone here with the black shales here, you can see a quite nice difference of temperature. And now, if we look here at the thermal imaging, how they change during the day. So they did 24 hours monitoring, and what you can see here during the day, I think I just need, okay, it starts to get colder during the day, and particularly in the Mars here. The Mars get quite warm during the day, and during the night it gets colder, and actually the Mars get colder during the night than the sandstones. So the amplitudes of variation of the temperature in the Mars is higher than in the sandstones. That's what the thermal monitoring was indicating. And when you are at the foot of the cliff in summer, during the afternoon, you can hear almost continuously small stones falling, small pieces of stones falling everywhere. And so this is what happens. During the afternoon, when it's very warm, the black Mars can reach almost 60 degrees. And you have plenty of small rock falls of few centimeters falling almost continuously. That's which makes that you have a preferential erosion of the black marks, which is a kind of thermal erosion. And when you have removed enough of material here, you have big pieces of sandstones following, so which falls afterward. And the pieces of sandstones are decimetric to cubic meters. But the small marks, which is the erosion of the small marks, are only very small pieces. It's really continuous. So that's a bit this thermal erosion here in sedimentary rocks. Another work which was done this time also in sedimentary rocks, but in limestone by Lidia Loiotine, and it was in Pogliano in southern Italy. You see it's a very nice cliff of different limestones with different colors. And it's quite touristic place, and she studied how thermal properties could influence the rock falls there, and how also it influenced the signal on the thermal images. So here is a thermal images of it. And what I'm going to show you is just a profile here on this slope. And this is the slope. This is the profile here on the left, the topographic profile. And she looked at the variation of temperature during the day along this profile, layer by layer. So there are different types of limestones and dollostones and of different colors. And she looked layer by layer, for instance, the variation, the range of variation of the temperature. Or hour by hour, she could make a profile of temperature through this column. And she compared it, for instance, to the GSI, the Geological Strength Index, to the fracture frequency, and to the porosity of the rock. And the main influencing parameters of the rock on the thermal images were the color, because the color is controlling the emissivity, the porosity, the fracturation, and the GSI. So that was part of a PhD. It's finished now, but I would say this work is just a preliminary work. And Federico Franzosi, who is now doing a PhD between Milano and Lausanne, is continuing this work, in particularly linking thermal images to GSI. He should publish a paper by the end of the year on this subject. So I am now going to show you another case, which is the detection of crack and karst. And this was done actually 10 years ago by Ivo Baron from Czechia. And Ivo is working on deep-seated gravitational landslides in Czechia. And he was one of the first to use thermal camera at this time. And he made a quite interesting work. So you see, there are some cracks there. And he went in winter, early morning, something like 6 o'clock in the morning in winter, when the temperature is very cold. It was -20, -30 degrees. And with the thermal camera, he was able to detect places where warm air is flowing out from the cracks. And that's quite simple, but he was able to detect here and there places where air is flowing out from the cracks. And he was even able to detect them from quite far away. And that can be interesting to try to reproduce this kind of studies with drone, for instance, with UAV. And here, he was quite far away, and he was able to detect with his thermal camera some air flowing out from this crack here that you can see closer. Yeah. So that was one of the first and of the first application of thermal camera to rock instabilities. And it works because there is a strong contrast between the air of the cavity and the ambient temperature. Finally, the last application I want to show you is what Weilio is doing here in Lausanne. He started in China and now he's working with us here on rock and using thermal cameras on rock mechanics. And he's trying to, what he did some tests and monitoring with thermal images. And this is one example, and you can see during the tests that the temperature changes, but look at the scale here. It's only 1 degree. It's only 1 degree of temperature. So it's not so much, but you could see the evolution of the crack during the test. Oops, sorry. So that's the work he's doing now. And we will continue this kind of research. Other research that we are doing here in Lausanne, but other people are also working on this in other groups, it's to use thermal images to constrain geotechnical characteristics, in particular to make the link between the thermal images and the GSI. So these are things in development. What Li-Fei in Lausanne is doing is to link thermal images with micro deformations, really to small scale deformation in unconsolidated sediments in marls and things like that. So coupling different ways to observe this deformation. And what we do also is to couple thermal imaging with ground-based INSAR. Ground-based INSAR is very, has a very high resolution for deformation. And it's really very interesting to see how some rock faces can deform every day due to change in temperature, and to couple that with thermal imaging. So the main challenges, I would say, in thermal images is that thermal images, they are not nice. They have low resolution. They don't have much pixels. And so the challenge, I would say, is to find application where thermal images bring something you don't see otherwise with normal picture. I have to say that I see a lot of paper where they say, oh, we have thermal imaging, thermal images. But when you look at the normal images, the RGB images, you see better than on the thermal images. So what's the use? So the challenge is really to find application where you can see things that you don't see otherwise, like the rock bridges of Antoine. And another challenge is, as I explained at the beginning, the temperature that you see on the thermal image is not the real temperature of the rock. And sometimes it can be quite different. And then you need to apply radiometric correction. Also, the first question is, do you need or not to apply this correction? And for instance, if the surface is made of one single material with one orientation, maybe you don't need. And to apply this correction, do you have additional data like contact thermometers, like reflectors? And do you have the geometry with laser scanning? And there is a large range of improvements of the thermal images that we can still try to do in future research. And that's it. Thank you for your attention. And if you have any question, I would be pleased to answer.